So welcome to Chapter 8. We're going to talk about how multiple processors work. We've talked a little bit about CPU scheduling and how we've gotten into, some algorithms on what's fair and how to make things compute. But it's interesting when you get to multiple processors, whether, you want to think about this as completely separate processors or cores in processors or multiple processors that have multiple cores. All of it kind of plays in, and you can define down to certain architectures and certain manufacturers of Intel, AMD, and even NVIDIA and GPUs, how we use these things differently. But what we're going to talk about today is kind of the basics of how you need to schedule and make things fair and make things kind of work, because the one thing you don't want to do is create some form of algorithm or some form of something where it runs and it kind of falls to some things we run into with things like splay trees and that, where it can get overloaded and a little lopsided, and now you've got everything crammed into one CPU and you might have 11 other ones empty. So how do we make sure that everything's kind of uniform? How do we make sure it's kind of fair? And then we'll take this from CPUs stitched together in a physical architecture to network, and I'll talk a little bit about that. And then in the end, talk a little bit about GPUs, because I think it's important to kind of understand how they're different and how we use them. They've kind of got their name in the whole Bitcoin craze that went on here a couple of years ago. Don't hear about it too much anymore, but if you just go look at NVIDIA's stock, you can kind of see where people kind of went crazy. And the thing that's cool with GPUs is that if you have a very specific reason for doing some form of compute, it's a great way to do it. It's technically meant for graphic processing. A lot of people took the G and made it general processing, which isn't true. But there's also other processors like DSPs, so digital signal processors that take a very specific codec. So coding and decoding a codec. And so like for voice, you would take something like a G711 codec and you'd take 8 bits to represent 8,000 samples a second, and so you kind of do all that math and you say, okay, the only reason for this thing to be here is just to kind of crank these things through. But they have very specific limits, like they can only do 12 channels at a time or 24 channels at a time, depending on how they're built. So we have different processors for different things, and we'll be talking mainly about CPUs because they're kind of the more general ones. To get into more specific technology around some of the other ones, again, we'll touch on GPU a little bit, but you really need to get to a point where you have a very specific need, and there's various things that kind of take from there. So kind of kick us off here. There's many different ways you can kind of connect all these CPUs together. And again, I want to step back and have us think about how data flows. Because I think you'll read in textbooks and people say it, data went from my hard drive to my process. Well, what does that really mean? Because data doesn't flow necessarily to the processor directly, to the CPU. If you think of the chain, we'll take the 3 easy steps. So you've got the actual CPU, you've got memory, and then you've got I/O. So let's just say disk. Could be sockets on network cards, whatever, and we'll talk about that later. But in those 3 things, again, there's a couple things we need to think about. There's a speed element, meaning that the hard drive is extremely slow, memory is pretty fast, and CPU is extremely fast. So they have to have buffers and everything in between them, so we've talked about that before. But I think, for today's lecture, it's really mostly important to understand how all those things relate and how you can use multiple of different things. Now, different hard drives have different queues, and they're just different places, and the code doesn't really care, but we usually treat all memory as one memory bank. Even if we've broken it up, as we've talked in virtualization in last week's lecture, doesn't matter, because you're going to break up, 2 gigs or 20 gigs or whatever for different OSs. But the CPUs, when you've got multiple CPUs, 2, 4, 8, dodecas, 24, 128, we have to think about how do they all relate and how do they work, because the CPUs are doing the work, the memory's storing the data and actually being the intermediary between, the CPU crunching code and doing calculations, moving things around, to how that then spits something back out to I/O and back and forth. So a lot of what we think about is we think about that bus, and we think about how that data flows. You're going to take that idea from that kind of physical to logical in how we do software development these days, and how we use different things like Kafka and ActiveMQ and RabbitMQ to really affect the logical flow of kind of what we're going to talk about today, which is more physical. So in all that, if you've got general CPUs kind of all over the place as an A, and you have just a shared memory pool, that's just one way to do it. You could have a different example, which might be something where you've got the CPUs, they'd each have their own memory. And this could be logical or physical. So we could say that every one of them's got its own, like they do have level 1, 2, 3, 4 cache in Intel as an example. But I think, for the sake of discussing it here, let's think about just different memory banks, whether they're physical or logical. But then you interconnect them, because sometimes you might have I/O coming in on one processor here that needs to talk to some process over somewhere else. So how do they talk to each other? And then when we talk about wide area, this whole internet thing, this is kind of what we talk about as distributed systems. This is the idea that you're going to have compute and memory that is treated as a unit more than it is kind of a functional function or algorithm or whatever it may be. And this is going to go do work. And so one of the easiest things to think about here is like things like BitTorrent, where it's not necessarily we're doing a lot of compute, but you might say that, out of these 6 devices, I want a file, and this file might be represented 1/6 on each of these. So I might be this, 7th thing out here asking for it. So I would ask for it, and these guys would kind of kick it down. Now, when you get to something that's, a little historical, but still kind of from an educational perspective, pretty valuable, is the whole concept of Hadoop and MapReduce. Hadoop is a distributed file system. So just, pretend you've got all these things out here. The file system doesn't give us that much, because that's what I just talked about with BitTorrent. But when you put Java's MapReduce on there, split those two things apart, map and reduce, what we can do with that is we can actually break down a function, and we can say, okay, I want this to be computed, but what I'm going to do is split it up into different things. And then the typical example would be if you've got a random number of words, and maybe they all represent fruit, I think is what it is. You would spit out chunks of this file to be computed to all these different computers out there, which is represented by the the compute and the memory out there, and they would summarize things. So mapping, getting a job out there, reducing it is the main thing it would do. So it could come back and say there was, this one might have added that there's 12 pairs, 2 pairs, 6 pairs, 9 pairs, and so you add all that up. Then there's 1 apple, 16 apples, 0 apples. And so it's a way for all these computers to kind of work the same at the same time. Now, the only reason why this works today, and it didn't work back 15, 20 years ago, is the internet was extremely slow. We went from modems to T1s, which is 1.5 meg. Anybody's got that at home knows that it's not great. It doesn't do that much. Maybe 1 computer, 2 computers is good. But now that we've got, massive speeds, 100 gig, we can start doing that, because what is the speed difference between some of these interconnected physical buses and this? Well, again, some of them are almost the speed of light, so not as fast as this, but when you get 1,000 machines all working together, that's kind of different. So we'll talk about this at the end, but we're just thinking about, how do these things get designed and how do they get built? Typically, it's more like A that has evolved to B, and then some things are more kind of like the C model, where this bus is just, like that interconnected, physical, gold or copper or whatever, medium to actually kind of transfer things back and forth. And it's kind of easy to see this, but there's a big problem in A right away is if you've got 2 CPUs and 1 shared memory, how do you make sure that they're not stepping over each other? What if they both at the exact same, microsecond wrote to the same piece of memory? That wouldn't work. So you need something in there to make sure that won't happen. But again, at this level, this is the lowest level we're ever going to get. You don't want to make some dumb mistake and say, well, let's go look it up in a big, huge table in memory somewhere. We want to have fast ways to do that. Now, cache is a different way that kind of does 2 things for us. You do get the benefit of the fact that the CPU talks much faster than memory. So when you're going back and forth, CPU is going to fill this up and then tell memory to go read or transfer. And it could be that memory is filling this up with an answer. And there has to be something to say, okay, CPU, I'm going to start here, and I'll tell you when I'm done. So there's that speed aspect of it. But it's also the fact that it's the same thing with character or block file I/O, is that we don't want to read and write or transfer stuff, a byte at a time or whatever at a time. So we want to transfer chunks. This last example is kind of the same thing, but does it make sense when we're doing bigger and bigger things to not deal with these registers down here, which are very small, but have private memory, which could be chunks of this, could be chunks of what we have as the main memory, or it could just be dedicated, but again, much larger. So instead of this being in the K range, the small meg range, maybe it's, 128 megs or, something that, is still extremely fast, gets everything done for me, but can calculate and get things pushed around faster. So again, we're always dealing kind of with these problems of what is the optimal block size of something versus a character size or anywhere in between. And then we're also thinking about the speed, how fast things transfer back and forth. It being that this is shared, this is going to be a bottleneck no matter what you do. So how do you make it so that maybe the CPU dumps a whole bunch of stuff up here, flips a interrupt and says, hey, I'm done, and now these two can talk to each other, but logically talk to each other and take it from there. So in this whole kind of sharing, this is the whole idea of UMA, uniform memory access, and how do we do that? And this actually came from some technology, back in the early I think around the time telephones were created, and the idea that you wanted some place for somebody to be able to call somebody else, but then know that they're being used. So if you've ever seen the old switchboard operators, or even some of the initial crossbar switches, the idea is really around closing this. Really kind of nails two things together. So this would kind of put this CPU of CPU 1 versus 2 versus 3, so don't get too lost in the binary here, but 1 now has this memory location. Now, obviously, nobody else on this can go through and say they have it, so it's kind of this thing of, kind of test and own in a way. This has been done in various fashions through different mechanisms and different ways for a long time. I don't say centuries, but maybe a century. And you can see these in some of the first kind of physical computers. You can see it in other forms of technology. We even see it in networking today. We see this whole thing of back when we first kind of started to have TCP networks, and it kind of started to really get hot. Let's say the early 90s. We had hubs. And everything was a shared medium, and you just threw your stuff out there, and the only reason it worked is there was a lot floating around. The more and more floating around, the more collisions you got, the more you would actually see there was a little green indicator light that would show you collisions. And, when the collisions happened, everybody stopped talking, and then they randomly started talking again, and it's kind of like, trying to talk walking through Times Square at a point, so that kind of falls apart real quick. So we went to switches. And what a switch is it's just a logical path that goes between two endpoints that only those two endpoints can see. So there's no idea or concept of, anybody kind of really kind of smashing together, right? From there, we kind of took it and said, okay, that's good, but look at the math here, or look at the, how much physical would you ever want to map there? Could you map, a K of memory? How do you want it chunked up? I mean, how does that stuff really kind of flow? Versus when you start to get to bigger things, just like we've talked about in file systems, like we've talked about in pretty much everything else we've talked about, once you start to grow to a certain size, you need other forms of ways to look things up, and it's usually not going to be, more physical things doing more physical things. So how do we achieve that? We can do it just like we've done it with other things, where when we went to virtual memory and we wanted to go, look things up, we did it in different stages, right? or different levels, I think we called it. And in going through there, you're going to kind of say a certain amount of bits, or however you want to represent it, would define the module, then the address, and the opcode, and value is just an example. So how are we plugging the right things in to then, go kind of push through and allocate and access memory? This gets even fancier with, different kinds of switching. So this is the omega switching network, just another example, and there's many, many, many different ways to kind of look at it and see different ways to do it. So this is 3 stages. So doesn't this remind you of something that we've talked about before? Multi-level, memory out, whether we're looking at paging in virtual file systems or or we're looking at trying to find some output value of something, whether it's through an MMU or whatever. We're going to have a fast way to look it up. And so this is just an idea that, why is this 3 stages? Well, it depends on how many memories you have, which is probably going to be much larger than the number of CPUs, but they could be the CPUs as well, but this is using 3 stages. Well, when this memory gets much, much larger, then maybe we use 4 or 5 stages. But the thing you got to think about as these things grow is to go from 1 to 2 stages is probably, like, let's say a 50% benefit. When you go to 2 to 3, that might only be another 20%. Or, and so they kind of aggregate down, because at a certain level you're not really gaining as much efficiency as you'd think, because you're just kind of splitting things down. So we've got uniform, this is non-uniform. And so this is kind of a different way to think about this. I think we talked about this a little bit in, I think at the end of one of the lectures on file systems, kind of the same idea. And this one is, since it's, single address space to all CPUs, so everybody can see everything at the same time, the access is via this load and store instruction. Now, think about that for just 1 second. If the access to remote memory is load and store, does that mean that it's a blocking call? We don't like blocking calls for all the bad reasons that come with blocking calls, right? So it's a way to do it, but sometimes you get benefit of that, because in the other example, you have to have these mechanisms where you're always kind of going through and looking things up, and you're trying to find things and map to things, and the different ways that you can kind of get access to things does create those collisions again. Even in a switching network, you have to, or in a switching network, in the switching network, you'd have to have something manage that and kind of go through and kind of say this is good and this is not good and wait. So the remote memory is going to be slower because of that blocking call, and that's why sometimes you hear those calls referred to as slow system calls. Means at one time it could be immediate and boom, you get it because it's there, and another time you're waiting for it and it could take microseconds, nanoseconds, could take a second, hopefully not, because that slows everything else down. So how this would work is we've got different nodes here, different ways to kind of lump all this stuff together, right? So I've got my CPU with my registers here, and then my private memory. And I've got 3 of these things. Now I've got a directory that can hold either things that I'm owning, things that are available, but this idea would be, if I've got 256 of these nodes, as it's explaining, I'm only showing, the ... there's getting you to the rest of them. How do these guys talk to each other? Now, it probably wouldn't be that if the CPU needed memory to go compute something and it had everything, it's going to go to its own memory. But it could be that a process came into node 1 knowing that node 0 is the one that has the hard drive controller. And so if I have to do I/O there, I have to do that. 255 might be a network card, and I may need to talk to that. So how do I flow this data back and forth? And this directory is really here to kind of almost act as, I wouldn't say it's like a directory in a file system, because that's just pointing to an inode, but it's really kind of more on that MMU style thing of saying this is in use or not, or this is here or there. But it could also be lookup tables, depending on how big that memory is. It could be multi-leveled as well, if it's very large. So many different kind of concepts in here. But and then this is what it would look like when you actually went to one of these tables, is how do you break things down? Now, yes, a directory in an OS in a file system, ext3, might look a little bit like this, where you've got a certain amount of bits held for the actual inode number, if that's 2, 3, 4, 5, 6, whatever size. Then you got the name here. This is kind of the same thing, but this is actually saying 2 to the 8th nodes. That's our 256 nodes. How many blocks? So each one can have its 2 to the 18th. And then the offset of where to go. So this is how you derive this whole size. Now you could take this 24 and figure out, how big that would be. But notice all of these put together is a 32-bit memory address. So this is a way to break these down like we've seen time and time and time again. We can break it down where every CPU has its own operating system. This is not necessarily the mainstay, and this is much different than we talked about last time with virtualization, because really what this is begging to have happen is forms of, and it would kind of be the mix between prioritization problem, where somebody's going to starve, and not really because somebody's going to always be going for the the most valuable, but it could be that CPU 3 with that private OS is just getting killed, and 1, 2, 4, everything else isn't doing anything. So as we kind of look at this, it's not necessarily the way you're going to do this for general operating systems that we have today. But it could be something for an embedded system. It could be something that we could leverage. We don't do it in phones, let's say, today, but we could if we want to get to maybe not breaking up CPUs but cores. If we look back in history, the IBM mainframe 370 days, I think if we went to, what was the other one I was just thinking about? Some of the Solaris Spark, the Sun Microsystem stuff. I think was able to do some of this, if I remember right, because they would actually have blades of CPUs, and I think you could mark out different OSs on them. I don't know if it was a full OS or more like the clone command, but it's a way to think about this. And so notice that they've got memory, which might be specific to different CPUs, might be broken out. You can kind of put a logical wrapper around this and say, well, couldn't it be though that if my Mac, which is on CPU 1, had 3 virtual machines of Windows, Ubuntu, and CentOS, that it would look like this, and you would do that? And it doesn't carve it up necessarily that completely. It does kind of dedicate a certain amount of CPU to the guest OSs as they're running. It does chunk these up this way, and it does leave I/O as its own kind of thing, even though there's kind of layers of, each of these now have to have their own queues versus this one kind of has more of the direct queue, and they have to talk to this one to get to this one, because it's kind of layered like that. But just again, something to think about, another way to do it. This is basically kind of looking at asynchronous, where it's not exactly the asynchronous model, but the idea that you could have one OS kind of running on one CPU and then all the other ones are just there to do work. And, again, we've got our memory and our, kind of broken up the same way you would normally. The thing you're going to lose out in is either one's going to be slammed because it's doing too much work and it can't dull it out to 2, 3, 4, or it's not doing anything and these 2, 3, 4 are getting killed and you're kind of wasting time. So again, you've got this other kind of concept in doing that. We normally don't load things asynchronous where we burn a whole CPU to kind of manage that, which is a little different than this. It isn't just that there's an OS per se here. It's just that the OS owns all of them, but its CPU scheduler runs different. If you ever want to, it's not the easiest code to look through, but it's kind of interesting to see what they did. If you go to kernel.org, you can just download the latest Linux kernel. rip it apart. And if you go into, I don't remember what directory it's in, but somewhere deep in the directory, you'll actually see, I think it's cpu.c and proc.c and some of these pieces of code where you can actually see the actual algorithms behind these things. So, and how they've kind of run. And if you want to change it, go ahead, see what happens. Interesting. Here's kind of more what we do today. So most Linux, I think by default, always is SMP, symmetric. And they all kind of, do the same thing. Now what's interesting is I wouldn't write this out like this because it makes it look like, all these things are in these buckets. The reality is they're kind of up here. They're all sitting here as a big user pool, and a process might use 2, and then it might use 3, then 1, then 1, then 2, then 1, then 4, then, you never know. It's however you've created the algorithm, and Linux's current one is defined as completely fair, so that's the algorithm. I think the previous one was big O notation. I was something about O. But, it's just ways of saying, well, how do you make things fair? I mean, what's the right criteria to make these things happen? So this is typically what we do today, and knowing that it's a little more fair in knowing that, as things kind of run through. It might be, though, and this is where you start to get into the minutia of things, that CPU4 does have its own memory and all of your stuff's there. So what we can do is we call affinity, or we create what we call affinity to that. So we can say, look, it might not be the most optimal, but it is, because moving your stuff around each one of these CPUs every time you want to keep working on your stuff is ridiculous. Because keep in mind, one of the premises of everything is preemption. At some point, somebody comes down, they say, okay, stop, get out of the way, somebody else needs to come through. Again, if you're standing in line at the grocery store and you're ringing out and you've got 100 items and you've got 8 and now you're done, it isn't that they just kind of kindly say, just step aside and let somebody through. They have to kind of kick you out, put you back in line, but they have to put you back with what's already been done. So the tape register with all of your stuff, don't think of the items really, because that doesn't matter, but you still have, 92 things of work you got to get done. You got to check them out. But you have to bring your tape, your receipt in, reload that. And so maybe it's not 8 items, maybe it's a huge sorting routine that's, using up 500 megs of RAM. And if it's doing that, and it's not this memory, and it's using it somewhat in the CPU, you would probably be better off creating that affinity and making sure it goes down there. And you could play games with pushing other things to different things, and knowing that, maybe you have a flag for somebody who has affinity and somebody who doesn't, and maybe the ones that don't go to different ones, and you can say that each one has a uniform 2 affinity, 1 and 2, so the next affinity is going to come to 3. So, it's all in how the algorithms are designed, but it's interesting to kind of think about, what applications would make that change. And the reality is that we haven't done much in computing that's changed much up until probably about 4 or 5 years ago. So back probably around 2015, 16, where distributed systems really kind of have kind of taken hold. We do compute much different now. The whole thing of microservices versus big chunky applications pushes things around and does different things as well. So the landscape of all this is changing. General OS computing is still fine for kind of what it does, but you can tell that it's not optimized, and nobody's really kind of looked back, because there's a lot of things that we don't talk about. Like, we don't talk about adaptive algorithms. Most algorithms don't look at what's happened recently and then they adapt and move to that. So take a file system as an example. So let's say that ext3 is 4096 bytes per block. That isn't some optimal number that somebody calculated across the world and said, this is exactly the right thing. It just so happens it just seemed to work that well, probably in a lab environment, and they took random amounts of data and they plugged it in there. But maybe ext4 is 8192, and that might not be the best one either. There's only one Veritas file system that actually, VXFS, that is variable sized, but it isn't optimized, it isn't adaptive, it just uses whatever it needs to. So I think about that a lot when I think about how people have kind of written these things. And, I think we've just had the luxury of being inefficient, but not inefficient enough to make a difference. So when we actually get to optimizing this stuff and thinking about how better we could, make these things, we could look back at some of these things and kind of change it. But keep in mind, why do you think we've got so many options? Because people have been trying to figure this stuff out for 50 years, 60 years, ever since the Turing machine. So, the stuff will evolve, things will change, but it's what we're trying to understand in this lecture is really what are the basis things I'm working on, and why do I need these certain things, and what has been done that hasn't worked, or and when it doesn't work, why doesn't it work? But symmetric is more a common way that's done today. But again, general compute, yes. When you get to embedded systems, probably what Tesla's cars are doing, you can make an argument that things need to be radically different, because if all I'm doing is sensing the left, sensor on the bumper, and there's 20 of them there, maybe I want to dedicate, maybe not a full operating system with a printer driver and all that junk, but I do want to have something that all its only job is to do that thing. That's completely different than having a Mac laptop and an OS on there and how that virtualizes. So a lot of that just goes into how we think about this. So I'm going to stop this one here and we'll start part 2.